relationship between the heap that is at hand and a tree that corresponds to that heap. So if we have a tree that in essence encodes the way the array is recorded in such a way that the element I, which is a node in that tree, would correspond to the two children, the left child, which would correspond to the element 2i in the array, and the right child to the element 2i plus 1. So if I am looking at let's just take an example. Suppose I have 6, 4, 5, 2, 1, and 3. Now let's verify whether this is actually a heap. Positions 1, 2, 3, 4, 5, 6. And so we have position 1 has to dominate, the content has to dominate what's in position 2 and 3, and that is certainly true. 4 and 5 are both smaller than 6. Then position 2 is 4, and 2 is 4 and positions 4 and 5, and 4 dominates 2 and 1. And position 3 contains 5, and that is dominates obviously what is in position 6, which is 3. So as you can see, this array 6, 4, 5, 2, 1, 3 is obviously not sorted. And so how does it correspond to a 3? Well, 6 of course would be the root, and then we have two children, 4 and 5, for that root, and then 4 has 2 and 1, and 5 has 3. That would be the corresponding representation of this array. In some way you can always take an array and convert it into a tree using the idea that for every node I, the two children are nodes 2i and 2i plus 1. Now, what that really then means is that effectively, when you have a heap, and that is now to connote the array, then you have a corresponding tree, which effectively is a complete binary tree, with the only possible exception being that some of the elements on the right end of that last row are absent. So this is, for instance, the case here. 5 does not have two children, it has only one child, and the other one is missing here, because a complete binary tree would have 7 elements. We have only 6, so obviously something has to be missing, and what is missing is something that is in this last right portion of the last row. Now, of course, if there were an element here, say 0, then it would that would be 7 and 0. That would be fine, but we're not doing that. So in this case, the tree is not a complete binary tree, but is about as close to a complete binary tree as it can get without really getting to a point where we are changing the height of the tree. So what you can derive from this array that satisfies this heap condition can of course also be done on the basis of the tree. In many cases we can sort of think in parallel, because in some cases it is more useful to use the tree than the array, because the tree is much more immediate. Now if we look at a tree, and that can be in terms of the array or in terms of the tree, what property can we derive? Well, it is surprisingly little that we can derive, because if you look at this tree, if you look at this heap, it is a heap. We verified that, but it obviously isn't sorted. 6, 4, 5, 2, 1, 3, there is nothing that is possibly sorted. And the same thing holds for this. This is clearly not a search tree. But what is it that we can state about a heap? Anything? If you look at this condition, what is it that you can say specifically about, say, the root of the tree or the first element of the array? Anything?
Dr. Lice, we're answering in the conversation to the, if you click on the little comment box, that's where we're answering your questions.
Why don't you just say it?
It's greater than all the others?
Yes, it is the maximum element. Okay, so the root of that heap tree, as well as the first element of the array that represents a heap, is always going to be the largest element of the elements that are represented there. So what that means is that effectively that is what we can exploit. So there are two issues we have to deal with. The first one is construct a heap, how to get a heap, and then how to take a heap and convert it into a sorted array. So the first issue about a heap is the following. Let's take the numbers 1, 2, 3, 4, 5, 6. So these are the positions, 1, 2, 3, 4, 5, 6, and let's just assume that these are the values. In some sense, if you start with an already sorted array, this is almost the worst case that you can get in heap sort. So, what do we have? Well, we want to satisfy this heap condition. This is what we're aiming at, and we have to make sure that that is actually satisfied. So if we look at these elements, well, what we have to do is we have to look at them backwards, from the end towards the beginning. And if we do that, then it follows quite clearly that the second half of that array, from 1 through 6, the second half vacuously satisfies the heap condition, because there is no twice 4. There's no twice 5. There's no twice 6. There's 2i, so if I is 4, 8 and 9 don't exist. If I is 5, 10 and 11 don't exist. If I is 6, 12 and 13 don't exist. So these elements without any further work, clearly satisfy the heap condition. In fact, we can populate this second half of the array any which way we want, and there will never be a contradiction to that heap condition. So what we then do is we're going to look at the next one, the one preceding that. So we have a 3. 3 is in position 3, which means we have to compare what's in position 3 with what is in position 6. Now, in order to achieve that, well, we have to get to that heap condition. And so the way in which we achieve that is by simply ruthlessly exchanging them. So instead of having 3 here and 6 here, we're going to put 6 here and 3 here. Now, what does that do? Well, it does guarantee that for the array from 3 to 6, the heap condition obviously is satisfied, because it from 4 to 6 we can put anything we want, and the element in position 3 now satisfies the heap condition, and as a result we have this a valid subheap, if you will. And so then we proceed to the next element, which is 2. So remember, we're going backwards from the back end of the array towards the beginning. And so we now have 2. 2 will have to be compared with what is in positions 4 and 5, which happen to be 4 and 5. And so that means that the larger of those 2 is of course 5. We simply get the larger of those 2, 2i and 2i plus 1, for I is equal to 2, and so that would be 5, and so we're exchanging 2 and 5. And again, because of this condition, it follows that nothing that we can do when we make this flip, when we exchange 2 and 5 to become 5 and 2, is going to affect whatever happened before, because these are simply different parents and children. And so in terms of that 3, we basically, what did we do in the first case? Well, let's just write down the original 3 that would correspond to the array that we started out with. We had 1, and we had 2 and 3, and then we had 2 is 4 and 5, and 3 is 6. So that would correspond to the array 1, 2, 3, 4, 5, 6 that we started out with, this array here. And so that would be the 3, using the same association between in